So in this video, we'll be looking at some other examples of a probabilistic method. And the first one we'll be looking at has something to do with tournament. So first, let me define what's a tournament. So a tournament on n vertices is a directed graph where every pair of vertices, let's call them xy, either x points to y or y points to x. So for instance, imagine we have a tournament on 4 vertices. Here are all the possible edges. Now let's just give a direction to each one of the edge. So this is a tournament. So one can really think about tournament in the graph theory definition as tournament in sports. So in this case, we can think about each vertex as a player. So we have players A, B, C, D. And we can interpret it, this arc as B beats C. And now we say a tournament has property Sk if for every set of K players, there's another player that beats all the K players. So for instance, if you look at a simple tournament with 3 players, this tournament satisfies property S1. Now let's check to make sure this is true. So what are all the possible subsets of 1 players? One can easily see that they're either A, B, or C. And for a subset of players A, then we can see that C beats A. Okay. Now for the set of players only with B, then we can see that A will beat B. And lastly, if the set of players only contains C, we can see that B will beat C. So an interesting question one could ask here is the following. So if n is much larger than k, does there exist a tournament on n vertices such that this tournament has property Sk? So the answer is yes. Let's write down the statement more formally. So if the number n satisfies the property here, then we know that such tournament will exist. So the proof here is actually very similar to the proof we have on the lower bound for Ramsey number. So essentially, we again want to use the probabilistic method, which means we want to show that a certain event will happen with positive probability. And so the event we're interested in is the following, which is that for every set of K players R, there exists another player who beats every single player in the set R. So again, let's write this event, this probability of this event as 1 minus the probability of the event complement, which is the following. So now there exists a set of K players R for which there do not exist any player who beats them out. Now let's call this event, which is associated with a subset of players R, event AR. Now one can write down this probability here as a union of smaller events. So when you take a union, you just need one of them to be true in order to have this being true. And this is exactly the same as just enough to exist one such set of players R. So now again, we can use the union bound. And we know that this quantity is greater than or equal to 1 minus the sum of all these probabilities. So lastly, let's just figure out exactly what is this probability here. So the event here, AR, is defined as the following. So every player will not beat all the players in R. So if you draw like a simple graph to help us understand this, so this is all the players, and we have the subset of the players here. Now let's consider just one player outside of the subset R. For this one particular player, the probability that he is not going to beat all of them here is exactly 1 minus the probability that this guy beats every single body here. And the probability that he beats everybody here is 1 over 2 to the k power. And that's because for each edge here, the direction will be going this direction with half of the probability and going this direction with the other half of the probability. Now, if we look at the probability for all the players out there, we achieve the probability this. And lastly, we can see the number of such R equals to exactly n choose k. And putting all of these together, we know this quantity equals to this. And because we have the assumption here, and we know this quantity is strictly greater than 0. And that's the end of the proof.